right, so we're going to talk about ions and bonding, um, and so we'll get going. And so just got an image there of ionic bonding between sodium and chloride, ions in solution versus the salt, sodium chloride, which you put on your fish and chips. And hopefully by the end of the class, you'll understand why when you put halite or salt on your fish and chips, it doesn't taste gritty. So I'll start off with the atom, and Bob's already gave us an introduction to this, but I like this diagram because what it shows is the conceptualization of how the atom works has changed through time. So going back to 1803, there was no real recognition that there was a nucleus, there was protons and neutrons. Atoms were just this solid ball, and they were considered the least or the most fundamental particle. And by the time we get 100 years later, people recognized, J.J. Thomson recognized that yes, these balls had charge, so the bulk of the ball had a positive charge, and there was electrons moving around within that. And then in 1911, we had the Ernest Rutherford, who decided that the electrons were orbiting around a central nucleus, which was positively charged. And then in Niels Bohr's model, which was more the sort of orbitals around us, sort of like planets around a sun. And then in 1926, it became recognized that actually these things are, yes, they're in orbitals, but they're probabilistic. So it's hard to, if not impossible, to know the location of a single electron, and we really have to think of it in probability terms. But nevertheless, we think of it as simple orbitals to simplify the discussion. And so I'm not going to go into this in too much detail because it's more than you really need to know, but just to recognize that within the atom, there are each electron is defined by these quantum numbers, the principal, the azimuthal, the magnetic, and the spin. And essentially what this means is no two electrons within a single atom can have the same principal, azimuthal, magnetic, and spin properties. And so as we progress in the number of shells or the n number, then we progressively increase the variability within the electronic configuration so that no two electrons can share the same properties. And that's really all I wanted to say about that. Now, Bob mentioned that, it gets very complicated, particularly.
You got a question?
Oh.
Yeah, I apologize, and this is getting a little intense, and you may not know it, but I was just reading about one element that has 8 different spins. I always thought it was just plus or minus 2.
It is plus or minus a half. But when you add up all the other properties, then you can get an increasing number of orbitals. Is that what you mean?
No, they claim that it actually has 8 different spins. That's why they use it in quantum computing.
Yeah.
Okay, that's fine. I just wanted to see. I just wanted to. That's fine.
I'll look that up. That's interesting. I'm just making a note here. I certainly didn't know about that.
They might be putting a different spin on things.
Very good. You could be a Canadian, Bob. So as Bob mentioned,
don't tempt me.
Yeah, I know. You're more than welcome. So Bob mentioned when the filling of the orbitals can get quite complicated, particularly when you get down to the rare earths. And so all this diagram is really showing is atomic number on the x-axis and the relative energy that it takes to fill those shells. And so really what I want you to get from this is if you look at cerium. So cerium represents an element where when we can energetically, cerium wants to fill the 4f shell before the 5s and the 5d. And sorry, let me rephrase that. No, that's right. Based on it having a lower energy profile. Okay. And so this is another periodic table that just shows kind of like what Bob showed with the rare earths, where he showed that they all start with the number of shells that a xenon has and then fills in from there. So this periodic table starts with 1s in hydrogen, and then as you go down, the lithium has the 1s and then also a 2s. Sodium has a, and so on and so forth. And so when we get down to the rare earths, we can see that they have the xenon filled up, and then we go along with the 6s, 5d, 6s, 5d, 4f, and so on. Okay, so just for your edification, if you ever wanted to know about how all the elements are filled up in terms of their energy shells.
Just to ensure your confusion.
Indeed, indeed. Well, that's to inspire further reading.
There you go. That's what I meant to say.
Okay, so what's an ion? And so an ion is obviously an atom which has lost or gained an electron. And so we call cations those that have lost an electron, and anions those that have gained an electron. The other word we sometimes use. What's that?
I mean, if we get cations, why wouldn't we call them the dog ions?
Yeah. Well, you'll have to ask. Maybe chemists just don't have a sense of humor. I'm not sure.
Well, they do wash their hands before they go to the bathroom. That's
true too. Just as a funny story, I once had a Texan do some groundwater collection for me in Canada, and so he had to go up to people's houses and ask to sample their groundwater. And he went up to one house, and this old lady took him out back to, she just had a dug well, and she threw a bucket into the well to get a sample for him, and pulled it up, and there was a dead cat in there. And she said, "Oh, there it is. I've been looking for him for 2 weeks." And so I asked Cody, "Did you collect the sample?" He said, "No, that it was contaminated." I said, "I know, but think of the cation analyses." But anyway. Now, sometimes we also refer to anions as ligands, and we'll get to that. Now, Bob mentioned the first ionization potential energy. So to make an ion, we need to remove an electron. And so the first ionization potential energy is the energy required to remove an electron from an atom. In other words, to ionize it. And so you can see that in this chart, the y-axis just is increasing energy in kilojoules per mole. It doesn't really matter. It just goes from hard to ionize at high numbers and easy to ionize at low numbers. And what do we see? We see a pattern where the noble gases are the hardest to ionize. And then the first column elements on the periodic table are down here, and they're the easiest to ionize. Within each periodic table, it becomes relatively harder to ionize.
And this ionization is to turn an element into an cation.
And to turn it into a cation.
That's right. We're never turning them into we don't have this graph for anions, although I imagine if you turn it upside down,
yes,
it would be something like.
Yeah, because that would be important as negative terms, for example, which we won't go into. Okay. The colored bars just represent the percentage of ionization of the different elements as they cross those bars. Now, then think in terms of, well, what would we do to make two ions come off an atom? And so we can think of the second ionization potential energy. And so the red one is the one we saw previously, and the blue is the second ionization potential energy. And all it's really saying is, again, to remove 2 electrons from an ion, from an atom, requires even more energy. Okay, and then that brings us to a concept called electronegativity. And so what's electronegativity? It's the tendency of an element to attract a shared electron when bonded to another element. Right? So if we think in terms of attraction, we have a cation gives up an electron and an anion receives the electron, then presumably the anions have higher electronegativity, and that's what we'll see. And so I'm going to show you an electrostatic potential map of a water molecule. And we all know the water molecule. The water is rather important to life on this planet. And you see it's not in a straight line. The hydrogens are at each other and compared to the oxygen. And then as we come across, this is just the electric potential. Really what we're seeing is where it's red, it's more negative, and where it's blue, it is more positive. And all this is saying is that the oxygen has a tendency to want to get the electrons from hydrogen. Okay? And that's so it is more, oxygen is more electronegative than hydrogen. So put another way, the behavior of elements in solids and dissolved in liquids is controlled in large part by how easily they give up electrons, okay, or gain electrons. So here's another view of the periodic table, and in this case, as you could call them, these rods, are scaled into the relative degree of electronegativity. I've covered the noble gases because the diagram was incorrect. The noble gases have no electronegativity because they don't gain or lose electrons without a whole lot of effort. But what we can see here is that fluoride, up here in the top right corner, where's my mouse? In the top right, is the highest element, and down here at the bottom, francium has the smallest bar or rod. Right? So this is a relative change in the electronegativity across the periodic table. And so, Linus Pauling, who died just 30 years ago now, he won. He's the only person to have won 2 Nobel Prizes in 2 different fields. So he won one for his work in chemistry, and then one for his he won a peace prize for his work trying to fight against the nuclear arms race. And so he came up with this electronegativity scale. It's a unitless scale. It just sets fluorine at 4, and everything else is less than that. And so we can look at electronegativity, which is the central plot here, right? And so again, we see that fluorine is 4, and everything else is lower than fluorine. And what you notice is that it's actually very similar to the first ionization potential energy in terms of its shape, right? So there's a relationship there between how easy it is to give up an electron and the electronegativity. The third plot just shows the relative covalent character, and we'll talk more about covalent versus ionic bonding, but again, the geometry of that diagram is very similar to the previous, to the upper 2. Okay, so electronegativity is crucial to determining bond strength and type, and so it will determine how an electron, where that electron exists preferentially with respect to the cation and the anion in question. And so the periodic table here just shows that, yes, fluoride has the highest, is the most electronegative, and francium down here in the bottom left is the least electronegative. And so basically we go from left to right and bottom to top, electronegativity increases. Okay, so then we can think in terms of the 2 main kinds of bonding. So we have covalent bonds and ionic bonds, which you all remember from probably high school chemistry. But we can think in terms of actually quantifying that using Pauling's numbers. And so where we have a bond difference, say between hydrogen here at 2.1 and fluoride or fluorine at 4, so the difference between them would be 1.9. And so if we have an electronegativity difference between 0.5 and 2, which hydrogen fluoride would fall into, we would call that a polar covalent bond. It's not purely covalent, it's not ionic, it's somewhere in between. Okay? Whereas the difference between potassium and fluoride or sodium and fluoride is much greater than 2, and so those would form ionic bonds. Okay? And then values that are less than 0.5, so say between aluminum and silica, a bond between aluminum and silica would be a covalent bond. Okay, so polar bonds create dipole moments, as I just showed with the water molecule. That was a polar covalent bond, right? And it influences molecular behavior. So, show of hands, actually just shout it out. So if we have sodium and chloride, 0.93 and 3.16 in terms of their electronegativity numbers, so what kind of bond would that have? Anybody want to guess? Or anybody want to calculate?
Ionic.
Ionic, right. And how about between hydrogen and oxygen?
Polar covalent.
Polar covalent. Silica and oxygen.
Polar covalent.
Polar covalent, right. Copper and oxygen.
How are you
Same.
getting how are you getting polarity out of these numbers?
How do you mean?
Well, water you showed us was polar covalent,
Yeah.
but silicon and oxygen, I mean, I can see how you've come up
Oh, no,
with covalent.
that's greater than, no, that's
Where do you
a
get the
covalent
polar?
bond. That's a covalent bond. That's right.
Yes.
That's
How
a
do you get the
covalent bond.
how do you get the polar part? Are
Well,
all covalent bonds polar?
no, there exist in a continuum, which I'll show in a minute. But you're right. The silicon oxygen bond would be on that definition would be a covalent bond. My mistake.
Yeah.
And
Thanks for
copper and
clarifying.
oxygen would be
Well, hold
covalent.
it. Isn't it 1.54 is the difference?
Oh, you're right. Yeah. Okay. Sorry, my brain's fried today. Yes, it
No,
would be polar.
agreed. Silicon and oxygen is covalent, but John, you said polar covalent. I'm asking, I'm not
Yeah,
Yeah,
that's
it's
contesting.
not greater. It's not greater than 2.
Yeah. So if we go
It's
here,
1.54.
yeah, but between 0.5 and
Oh,
2, it is polar covalent. Yeah.
oh, okay. So
Yes,
it's not polar. The word polar belongs to covalent, not polar ionic.
that's right.
Okay,
Yes.
I got you. Now I'm with you.
Now you're with us. Okay. And so we go down polar covalent, polar covalent. What about copper and copper?
Covalent.
Yeah, it'd be pure covalent, right? Because they would have the same electronegativity. Okay, very good. Sorry for that confusion.
And just to clarify, when you say strength of dipole, if the atomic difference in electronegativity is close to 0.5, is that dipole stronger or weaker than if it's
That'd
1.9?
be a weaker dipole, and then as you get closer to ionic, it would be a stronger dipole.
Okay, so water is 1.2.
Yeah, so
So
somewhere
that's kind of in the
smack in
middle.
the middle. Yeah,
Okay, thank you.
perfect. Okay, ionic radius. So what's important about the ionic radius is it controls this bonding, and as we'll find out as we go along in the course, it very much controls how different elements, how different metals substitute into different minerals, right? So positively charged atoms have a smaller ionic radii than negatively charged ions. And so the ionic radius decreases as charge increases. And the reason for this is if you think about an atom, we've got the nucleus is got a very positive charge and the electrons have a negative charge. And so they're in balance. So if we take away an electron from a cation to form a cation, there's less negative charge, and so the nucleus is going to pull the electrons closer to the nucleus, right? Equally, if we take that electron and add it to an anion to make an anion, we've increased the negative charge, and so the size of the ion will actually increase because now there's less pull from the nucleus. Okay, and so here's another chart that just shows basically the ionic radius of the different elements, and you can see as we increase the number of orbitals, the ionic radius gets bigger. That makes sense. And as we go from left to right, the left hand and the right hand side have the largest ionic radiuses because they have the least number of electrons given up or accepted, and then the transition metals and the rare earths have the lowest, the smallest relative ionic radii. And so this is just a simple chart. So here in gray is the atom. So the left-hand 3 columns are in red, and so the red ball is the cation, and on the 2 right-hand ones, the blue ball is the anion. And so all this is showing is that as we ionize, take lithium atom to lithium ion, we decrease the ionic radius from 134 picometers to 90 picometers. Conversely, if we take fluoride, for example, or fluorine and create fluoride, we'll increase the ionic radius from 71 picometers to 119 picometers. Okay. And you can see as we go down, say group 1, lithium, sodium, potassium, rubidium, the ionic radii increases. Okay, so what's bonding? So bonding is when we join 2 or more elements or 2 or more atoms together, right, to make a molecule or a compound. So a stable compound occurs where the energy of the compound is lower than that of the individual atoms. In other words, nature tries to get to the minimum energy state, and so where joining two elements together to make a compound lowers the energy state, it's likely to happen. And so the bond state implies a net attractive force between the atoms, right, which is sharing electrons. So we've got a negatively charged anion joining up with a positively charged cation. So that forms a chemical bond. And we've already talked about, we have the 2 major classes of bonding, our ionic bond and the covalent bond. So in an ionic bond, in a pure ionic bond, there's a total transfer of electrons from one atom to the other. And so that's depicted in this diagram where we have a metal atom wants to give up its electron to go to the non-metal. So, and then we end up with an ionic molecule where the electron is mostly sitting around the anion and not around the cation. In covalent bonding, there's more of a mutual sharing of electrons. Water, CO2, SiO4, 4-, etc. Right? So these tend to be good conductors of heat, but not electricity. I should have mentioned that. Ionic bonding are good conductors of heat and electricity and have high melting temperatures. Tend to be hard and brittle, but also very soluble in water. And so covalent bonds make molecules that are harder, less brittle, and less soluble. And that makes sense. If you drop a cube of halite into a glass of water, it dissolves. Drop a cube of quartz into water, it doesn't dissolve. Well, not on any meaningful time scale anyway. And so this is just depicting what a covalent bond looks like. So the cation and the anion are sharing those electrons equally in a pure covalent bond. But it's, as we just discussed with electronegativity numbers, we have a continuum. So on the left-hand side, we have a pure covalent bond where the electrons are shared equally. And on the right-hand side, we have a perfect ionic bond where the electron is shared, where the cation gives it up completely to the anion. And then in between, we have these things that are more polar covalent. Okay. So we also have metallic bonding. So even though ionic and covalent are the most common bonds, we have metallic bonds where the valence electrons are mobile. So they're not actually sitting around a particular atom. They can move freely within the lattice. And so all the metals share those electrons. Okay. And as we know empirically, metals are strong conductors of heat and electricity. There's a fourth type of bonding called van der Waals, which is an electrostatic bonding and results in an asymmetric distribution of charge. And so what happens is we have two atoms, and in van der Waals bonding, the negatively charged end wants to align with the positively charged end of the other atom.
So biotite is a good example of that, right?
Yes, yes, it is.
So
Where the sheets,
yeah,
the sheets. Go ahead.
that's probably the best example we have of van der Waals bonding that we can all, touch and go, oh, because it's so easy to separate sheets. The people in Moscow used to use big sheets of mica, and that's why we call it muscovite.
Yeah, used to be windows.
Yeah.
Yeah, perfect. Okay. And then finally, we've got hydrogen bonding. So it's an electrostatic, it's like van der Waals, it's an electrostatic attraction that occurs exclusively between hydrogen and more electronegative atoms, such as oxygen, nitrogen, and fluorine that we've already talked about. Okay, so it can be slightly stronger than, I guess, several orders of magnitude stronger than van der Waals forces. So it's an intermolecular force, not an intramolecular force. So it's between molecules, not within molecules. And so we can think of it in terms of water molecules. So here we have a series of water molecules, or as some people call it, dihydrogen monoxide. And what we can see is there's an attractive force between a hydrogen and an oxygen between water molecules, and those are the hydrogen bonds. So what it does is it gives an orientation and an arrangement between water molecules, and this is why we can have liquid water. Okay, and we're going to talk more about this next week when Bob talks about Goldschmidt's rules. But the substitution of elements for one another in geochemical systems. So, for example, if we take a mineral like I can't think of one right now. Take a mineral like pyrite. So pyrite's got 2+ iron in it, and so things like nickel with 2+ can substitute into pyrite structure because the charge of the ions is the same, they have a similar ionic radius, and they form a similar bond type. And that's it for this lecture.